All right, I want to do an example of a kinetic and thermodynamic addition. And so we're going to run this reaction where we start with this conjugated alkene, conjugated system, and we're going to react it with H plus and H2O. And we're going to do this and kind of predict what is the kinetic product, what is the thermodynamic product, and then we'll look at conditions for all of that, right? So the first thing we need to do whenever we have this, right, is we need to do two things, right? So we need to first figure out which cation is more stable, right? How do we make the most stable cation? And then two, which product is most stable, right? So obviously those are going to correspond to the kinetic and the thermodynamic products because as we said before, the thermodynamic product is going to be the most stable product where the alkene is attached to the most carbons, and the carbocation that's the most stable is going to correspond to the kinetic product, right? The product that results at low temperature goes through the most stable carbocation. So the first thing we have to figure out is where is the most stable carbocation. And that's not necessarily always the most straightforward thing. We have two double bonds that can react with H plus. So we have a couple of different options. So where do we want to put our carbocation to make it the most stable? Well, remember the things that make carbocations stable. Stable carbocations have one, they have substitution, right? So tertiary carbocations are more stable than secondary or more stable than primary. And secondly, they have resonance. If we can resonance stabilize a carbocation, that is going to make it more stable. So especially in conjugated systems, we want to incorporate both of these things. Right? So we have our conjugated system. There are 4 carbons in our conjugated system. I'm going to number them 1, 2, 3, and 4. Okay? Just so that when I refer to them, I don't have to gesture at them with my pointer, right? So we have carbons 1, 2, 3, and 4. That's part of this. In order to get resonance, right, our carbocation needs to be on carbon 2 or 3. Cation must be on C2 or C3. Okay, and to prove that, right, I will say that if we react this carbon-carbon double bond that's in the ring with H plus, we would put the H plus on carbon 1, make the carbocation on carbon 2, and we would have resonance stabilization with this other double bond. Right, so that's carbocation on C2, or right, we could, well, I'm going to do this in a different color just because I can through the wonders of technology. Or right, we could have the other double bond, the C3-C4 double bond, nope, get H plus like that, and then that would give us, we put the hydrogen on the primary carbon here, have the carbocation on C3, and that would be resonance stabilized by the other double bond. Right? So both of these are resonance stabilized. The question is, which of these two is more stable? For that, we turn to substitution. Now, this will always be true. We always want to put the cation on kind of the internal carbons of our conjugated system, carbons 2 and 3, because that's the only way that we can have resonance. And resonance is always going to lead to the most stable carbocation. So we'll always put the carbocation on carbon 2 or carbon 3. Now we just need to figure out which of these is the most stable. We have a secondary cation here, stabilized by resonance, or we have a tertiary cation here, which is stabilized by resonance. So given that choice, substitution tells us which we think we should prefer, right? And we would prefer that, or we would note that this is, whoops, I guess I've changed colors again, that this is the most stable cation, right? It's tertiary, plus it has resonance. All right, so we've answered question 1. What cation is the most stable? It's this one. So now, our mechanism, as we draw it, is going to be, we're going to have the carbon-carbon double bond between C1 and C2 come get H plus. We're going to make the carbocation at the tertiary carbon. Hydrogen's been added to the secondary C1. And now we have resonance. So we need to draw in those resonance forms because we have to figure out what the possible products are. Right? The resonance forms are going to be this tertiary cation that we already drew and the primary cation that is its resonance form. Now, you're probably thinking primary cation, that's terrible, we don't want that at all. And that, if we were just looking at stability of carbocations, clearly this is still the most stable, right? The tertiary carbocation is the most stable one. But remember that when we consider the products, it's not the stability of the carbocation that determines which product is more stable. So now each of these is going to undergo attack by H2O, right? Because we have two resonance forms, both of these things exist. They're both going to be attacked by H2O. So let's take the most stable one, react it with H2O. Water attacks the carbocation, and we get, I'm going to throw in a minus H plus in there just because I don't want to draw these things too many times. And here's one possible product. We could get, this is the 1,2 addition, right? The hydrogen is added to carbon 1, the OH is added to carbon 2. We get that, right? The other option, of course, is we could go from the less stable carbocation intermediate, add H2O, lose H plus, H2O will attack the carbocation here. We'll end up with a primary alcohol and a 1,4 addition, right? The hydrogen is added to C1. We have a double bond in the middle here, and now we've got a primary alcohol on C4. Now we compare these two. We have two alkene products. Which of these is the more stable product? We look at how many carbons is the double bond connected to. In our 1,2 addition, the first example, coming from the most stable cation, you see that the carbon-carbon double bond is only connected to one other carbon. So this is a mono-substituted double bond. Over here, we have 3 carbons connected to our double bond, and so this is going to be a tri-substituted. So if I look at the double bond here between C2 and C3, we're connected to this carbon, and this carbon. Those are the 3 carbons that we're using to call this a tri-substituted carbon. That means the tri-substituted alkene is going to be more stable than the mono-substituted alkene. The tri-substituted alkene is the more stable product. Right? So we have the product that results from the most stable intermediate, which in this case is the 1,2 addition, giving us the tertiary alcohol. And we have the most stable product, which in this case comes from the less stable intermediate, a primary alcohol with a tri-substituted double bond. So if I gave you conditions that said, for example, take this conjugated system, H plus H2O, and run this reaction at 0 degrees Celsius. You could predict, we have 2 possible products. We have, which we've already figured out, so I'm just going to redraw them. If this doesn't look familiar, return to the previous slide and make sure that those mechanisms make sense. We have 2 possible products. This one and this one. At 0 degrees Celsius, we note that that's low temperature. And so that means the kinetic product will be favored, which means, so I'm just going to keep adding things here, we're going through the most stable cation, right? The kinetic product is the one that goes through the most stable intermediate, the most stable cation. That is this one here. So we would expect to see the tertiary product, tertiary alcohol product, as our main product at 0 degrees. If I gave you the same reaction, but instead we were running it in boiling water, right, you would expect to see, so you'd have still the same 2 products possible, but you would expect to see the thermodynamic product as the dominant product. And so in this case, the thermodynamic product is, of course, the one that is the more stable product. So we have high temperature. High temperature implies that we're going to find the thermodynamic product. The thermodynamic product is the most stable product. And so we consider this one as the most stable product. Right? So that's the process. Now, I want to point out that we don't ever consider this other carbocation. Once we have to, the H plus can only add in one place, right? So we can only make either the cation at C2 or the cation at C3. Once we make the cation at C2, we still have options because there's resonance there. But we find the most stable cation first, draw the resonance structure of that cation. Those are the two things that lead to our two products. Once we've made those products, we will always have kind of two options. The most stable carbocation will lead to the least stable product because the most stable carbocation puts the cation at the most substituted position. The most stable product puts the alkene at the most substituted position. And so you can't have it both ways, right? Either you have the cation at the tertiary position or you have the alkene at the tertiary position. You can't have both. So they'll always be different products. The kinetic product here, the monosubstituted alkene, or the thermodynamic product, the tri-substituted alkene. Right? That's one example. Stick around and we'll do another one.